Hello my people, I hope we're doing well today. As promised, optimization videos. Some of these will look familiar, a couple of them we did in class, and I will redo them simply so that we can have a more thorough explanation of the problem. Felt that some of them were rushed either in class in person or the videocast classes that we've had thus far. Let's go ahead and start with this one. It says a person in a rowboat 2 miles from the nearest point on a straight shoreline wishes to reach a house 6 miles farther down the shore. If a person can row at a rate of 3 miles per hour and walk at a rate of 5 miles per hour, find the least amount of time required to reach the house. How far from the house should the person land the rowboat? Okay. Well, there's two questions here, but basically it's just one scenario, and it's not going to take all that much more time to answer two questions than it is to answer one. Now, remember, not an artist, never claimed to be one. But there's our dude in the boat. He is 2 miles from a straight shoreline, and then 6 miles down the shoreline, we have a cute little house. So we have 2 miles from shore, and we have 6 miles downshore, right? And the idea is that he's probably going to be aiming somewhere in between this point right here where he's straight, this point on shore that's perpendicular to where he is, and going all the way home in the boat. And we need to designate which is which. Now, there are two different ways you can do this. You can designate this as x and this as 6 minus x. Now, if you designate this as x, the advantage is that x will be how far from the house the person should land the rowboat. But if this is x, you have the benefit of having a simpler radicand, because if this is x, then this is x squared plus 4 rather than 6 minus x squared plus 4, right? And so you have 6 minus x. And I'd prefer to do it this way. You can do it either way, though. Now, we are trying to minimize time, right? It says find the least amount of time. So we know that we're dealing with distance and rate and time, but we need to transform this formula such that its time is equal to distance over rate. Or, the way we're probably going to do it is the reciprocal of rate times the distance. Alrighty. Well, we know that this square root right here is basically the distance he spends rowing, the distance rowed. So basically the time spent rowing, and we'll just do T sub R for time spent rowing, is going to be that distance divided by 3, because that's the rate at which he rows, right? Now, thankfully, we don't have a disparity in terms of units, right? You were given miles in terms of the distances, and you were given miles per hour in terms of the rates. So that's all well and good. And so it's 1/3 times x squared plus 4. And then we have the time spent walking, and that's 1/5 times 6 minus x, or, if you want, 6/5 minus 1/5 x. So the total time that's spent in transit from his spot over here to the house is going to just be the sum of those, right? And I'm going to turn the radical into parentheses with a fractional exponent to make it easier to do, and I'm going to flip this linear around into descending order so that when I take the derivative it's going to be easier, or just cleaner. So basically what we have is we have 1/3 times 1/2. Now I could have turned that into 1/6, but we'll see in just a second why I'm not going to do that, because I now have a 2x as the derivative of the inside for my chain rule, and of course that 2 and that 1/2 are going to cancel out. And then all that I have from the linear is the minus 1/5. Now if I simplify this and set the derivative equal to 0, I'm going to have x over 3 times the square root of x squared plus 4 minus 1/5. Well, I'm just going to put the 1/5 on the other side anyway, so let's go ahead and just change that negative sign to an equal. And now I have a proportion and I can cross multiply. Okay, well, at this point I'm going to need to square both sides the way that I often do with a radical equation. I know that this 3 when squared is going to be a 9, and I'm going to distribute it across the x squared plus 4, which when squared is going to lose its radical. And I'm going to get 9x squared plus 36. Let's go ahead and subtract both of those over to this other side. And I can pull out a 4, and I'm going to get 4x squared minus 9, or 2x plus 3 and 2x minus 3. The only one that's this one is going to give me a negative x value, but this is going to give me x is equal to 3/2. That's my critical value, right? Okay, well, here's the thing. This is not one of those problems where we're going to have to use the first derivative sign chart and evaluate using the first derivative test. And the reason is that you're on a closed interval. This is more like those problems from 4.1, because x can only take on so many values. X, by its very nature, has to be between 0 and 6. So what we're going to do is we're basically going to evaluate it as an extrema on a closed interval. Okay, and that, like I said, is reminiscent of 4.1 in our books, and that means that I'm going to evaluate time at t is equal to 0. Okay, now time t is equal to at x is equal to 0 is basically the scenario where this dude rows straight to shore and then walks. Okay, there's no angle to his rowing trajectory. Then I'm going to evaluate t of 3/2. And then I'm going to evaluate t of 6, which is basically how much time it takes if he just rows straight towards his house. Now, t of 0, if I go ahead and look at this t of x that I have, I'm going to go ahead and plug in t of 0, and I'm just going to get 1/3. The 0 is going to get squared. I'm just going to have 4, so it's basically the square root of 4 right there. And then if I use this version right here, instead of it having been distributed and reordered, what I'm going to get is I'm going to get 1/5 times 6. Okay, well that winds up being 2/3 plus 6/5. Well, if I get a common denominator, that's going to simplify to 28 over 15, and I get 1.867. All right, let's do the 3/2. I get 1/3. Now, when I square 3/2, I'm going to get 9/4. When I combine that with the 4 with a common denominator, I'm going to get 25/4. So it's the square root of 25/4. Now, when I take 3/2 and I plug it in right here, I'm going to get 6 minus 3/2. Well, that's going to be 9/2. Okay, so I have 1/5 times 9/2. Now, when I simplify all of this and then I get a common denominator, I'm going to get 26 over 15, which is approximately 1.733. Now, when I plug in 6, I'm going to get 1/3, and I'm not going to get something nice under the radical. I'm going to get 40. But I don't have to fool with this because 6 minus 6 is going to be 0, so it's 1/5 times 0. And so really what I get is I get 2/3 times root 10, and that is 2.108. This right here is my min, okay? Because both endpoints represent a longer duration of time. Now, let's go ahead and answer both questions. I was basically told that I needed to find the least amount of time, okay? Basically, the least amount of time is 1.733 hours, and he should land the boat 4.5 miles from the house. And asked in sentence form, answered in sentence form, and there we go. Now, I want to do one more that is similar to this because there's something a little bit funky about this example, okay? Now, this one right here says you need to reach home as quickly as possible, but you're in a rowboat 4 miles from shore. Okay, let's go ahead and sort of draw that perpendicular to the shoreline. You are 4 miles from shore, and your home is 2 miles up the coast. If you can row at 3 miles per hour and walk at 5 miles per hour, toward which point on the shore should you row? Toward which point should you row if your home is 7 miles up the coast? Well, let's go ahead and ignore this second question right here. Let's just focus on that first one, okay? Now, I notice that if this is x and this is 4, then this is the square root of x squared plus 16, just a little bit of Pythagorean theorem. And this is 2 minus x, this distance between this point, which they're calling P, to home. Again, I'm going to be using the formula of distance over rate, and I'm not going to break it down. I'm just going to go ahead and do it. Now, I know that the distance that person rows is x squared plus 16. Now, the rate at which the rowing occurs is 3, so we divide by 3 or multiply by 1/3. Now, it's going to be 1/5, that's the rate at which the person walks, and 2 minus x. Now, if we take the derivative of this, we're going to get 1/3 times 1/2. Again, not combining it because that 1/2 is going to cancel here in just a second because of the 2x, right? And then minus 1/5. That's the derivative. Those cancel out. And what I'm left with is x over 3 times the square root of x squared plus 16 minus 1/5. Well, again, all I'm going to do is shove the 1/5 over to the other side, save myself a little bit of space. Let's just turn it into the proportion that it's going to become. Now I'm going to cross multiply. Then I'm going to square it. Okay, well, the 16 is going to be multiplied by the 9, right? Which is going to be 144. Okay, so what we're going to get is we're going to get 16x squared minus 144 is equal to 0. Well, 16 is a factor of 144. It goes in 9 times. So it's x squared minus 9 is equal to 0. So my critical values are x is equal to positive or negative 3. Now I'm used to throwing out the negative x value, but in this one you need to throw out the positive x value too, because x has an interval between 0 and 2. The positive one is not on my interval either. So the minimum time is basically going to be one of the endpoints. And so what we need to do is we need to evaluate t of 0, and that's going to be 1/3 times the square root of 16, which is of course 4, and then 1/5 times 2. Well, that's going to be 26 over 15, and we know that that is equal to 1.733. Then let's go ahead and evaluate t of 2. Well, that's going to be 1/3 times the square root of 20 plus 1/5 times 0, which basically winds up being 1/3 times root 20. You could pull it out and make it 2/3 times root 5 or something like that. But if you're going to get a decimal approximation anyway, it doesn't really matter. So you have 1.491. That's the smaller number. That represents the scenario where the person should just point the boat straight towards home and row, And that's basically what you're going to say. Row straight home, or something like that. Okay? Now, that basically, I wanted to show you both of those scenarios, one that was straight up and another one that was going to basically throw a curveball at you, because we do need to be constantly making recourse back to the interval. And on most functions, obviously, what we're talking about is the domain, right? And so if you, and thing is that if we don't go through enough examples like this where there are problems, then you're going to get to the test or whatever assessment and assume that that sort of scenario has created, basically as an indication that you've done something wrong. And in this case, it shows you that you haven't, okay? In the next lecture, we'll do a couple more problems. There is not really a common theme to the next video, except for, you know, I guess a little bit of trig. But if you have any questions, as always, please do shoot me an email. Bye.